Hi, all. Thank you for coming. I hope everyone has had a great start to the conference. This is Brad Kaiser. I'm Craig Ingram. We're here today to talk to you about supporting highly multi-tenant Spark notebook workloads. A lot of what we're going to talk about today really applies to more than just notebooks, but the key distinction here is that notebook workloads typically involve sporadic delays mixed with periods of unpredictable activity. In this talk, we'll share some of the pains we've gone through, as well as some of the different architectures that we went through along the way. We hope you leave this room having a more complete view of what it takes to successfully host highly multi-tenant Spark notebook workloads. Now we'll talk about our journey a little bit. We started using Spark at TWC at the tail end of 2014. At that time, we were mainly writing batch jobs to support solving many of our business needs. Over time, we started using notebooks more and more for lightweight discovery and analytics and reporting. This is outside of our traditional BI tools. When IBM bought TWC in February of 2016, we shifted focus to building and supporting a platform using Spark as the cornerstone for batch analytics. It probably comes as no surprise to you that there are many groups at IBM that are using Spark to help their customers solve problems. In fact, we have several public offerings of Spark. We have the IBM Analytics for Apache Spark, or Spark as a Service, and the IBM Analytics Engine. This is used in our data science experience and Watson Data Platform. We'll talk more about those in a little bit. These platforms may sound similar, but they're very different underneath the covers, and their offerings and differences are beyond the scope of this talk. But the problems that were encountered by these platforms are what propelled us to actually investigate some of the topics that we'll talk to you about today. But I'd also like to take a moment to talk about IBM's commitment to open source. Not only is IBM a founding member of the Apache Software Foundation, but we have over 180 project committers across 77 different projects. In the context of Spark, our goal is to contribute intellectual and technical capital to make the core technology enterprise and cloud ready. So what's our mission? We want to host a secure, performant, and stable platform that will enable interactive analytics, visualizations, and reports. It's essential to provide collaboration tools and job scheduling capabilities as well. The platform should serve as an easy launch point for new users of Spark so they don't have to learn all the ins and outs of all the different components involved in the ecosystem. So the goal here is to host a platform that supports hundreds of analysts and data scientists. The platform should allocate kernels in less than 10 seconds, so users aren't waiting around for the paragraphs to start executing. One of the issues we've faced in the past is severely over-provisioning our clusters to meet SLAs and support workloads being run. This leads to inefficient resource utilization. In the new world, we want to support dynamically scaling the number of nodes in the cluster to reduce costs and to more effectively utilize the resources that are actually available in the cluster. At this point, I'd like to turn it over to Brad to talk about some of our lessons learned.
Thanks, Craig. Hi, I'm Brad. So I'm going to talk about our journey at the Weather Channel and some of the lessons we learned. Back in 2014, when we started doing this, we knew we had a lot of customer data that we weren't really doing anything with, and we wanted to start gathering that and analyzing it. So we knew we needed a Spark cluster. We knew some of our data was going to be sensitive, and we had some hard, corporate requirements to be cloud agnostic. So we decided to build our own cluster. So to start out with, we had one big production cluster co-located with Cassandra, and this was fast and stable. It was just our team, and we were doing a lot of ETL jobs because we were still kind of figuring out what kind of data we wanted to get and what we wanted to analyze. All of the analysis was being done on our team, and everything was being scheduled by our team. So this worked really great, and it was super nice. But over time, some other teams started to become interested in the data we were gathering. And this was great. This is what we wanted to happen. But as we opened up our cluster and started providing notebook services, we realized there were some problems with this architecture. First, it was very easy for outside users who had kind of a range of data science and programming experience to crash our cluster and ruin all of our ETL jobs, which was an incredible hassle for us. What would happen, people would just use a ton of resources without realizing what they were doing, or they would just know what they were doing and do it anyway, and cause us a lot of problems. We also had an issue that all of our data access privileges were just wide open for the whole cluster, which was fine when it was just us, but as we started getting more and more data and more people using it, it was starting to be kind of a problem. So our first solution was we thought we would just add some small clusters. So we built some small clusters for some other teams at the Weather Channel, and that was great. It was really easy to do, and it stops people from bringing down our production cluster. But this had some pretty big problems. So the big downside was setting up all these clusters was a real hassle. The first one or two was fine, but after a while it gets pretty old. Also, we had to do a lot of maintenance work, which eventually started to be the only thing we had time to work on. Also, another problem was we had a lot of duplicated functionality with this setup, which resulted in idle servers, and also access privileges were still pretty coarsely grained just based on your cluster. Eventually, we were able to relax our requirement to remain cloud agnostic, and we started using Elastic MapReduce. So our analysts were able to set up ad hoc clusters and do what they wanted without messing with us, and that was awesome. But we still had some issues with this architecture. First, it put more of a burden on our analysts because they had to figure out how to set up EMR clusters and do that, which isn't hard, but it's certainly more difficult than just opening a Jupyter notebook. Also, we had less insight into what analysts were doing, and we didn't have any kind of central management or data governance for what was going on. And finally, our analysts just tended to start these up and then leave them running, which wasted a lot of money. So I also want to share with you some lessons we learned that were learned by our colleagues at IBM. So first, to explain one of our offerings at IBM, we have this cool notebook offering called Data Science Experience. It combines Jupyter notebooks with collaboration tools, so your data scientists can share notebooks and data sets and comment on each other's work, and there's a GitHub integration, and there's extra libraries on top of everything that make it a little easier to use. So that's great. And on the back end, it can run in the IBM cloud or your cloud or on your IBM mainframe, whatever you want. So that's great, but we had some issues bringing this together. First, Jupyter isn't really architected for this sort of workload. With the Jupyter kernel gateway, everyone's kernel and Spark driver end up running on the gateway server. And if you're trying to support a lot of users, this quickly becomes a big bottleneck. So what are the lessons we learned at IBM? So the big lesson we learned is that you need to move those kernels and Spark drivers off the Jupyter gateway. We call this kernel remoting, and this lets us run all those collaborative tools we were just talking about in your application tier and move all those kernels and Spark drivers into our analytics tier. Some other issues we have by running a big analytics tier, the first is starvation, and this is when a user joins a cluster, grabs a bunch of resources, and then holds them and prevents other users from being able to take them. Another issue is cache data. So obviously, cache data is very important for getting good performance out of Spark. But the problem is, if data is cached on an executor and you want to shut down that executor and reclaim some of those resources, you either can't do it or you lose that cache data. And finally, we just would find performance bottlenecks in Spark, which just happens when you have a lot of people using a service. For example, we just had an issue where we had someone had a job that generated a huge amount of tasks, which would cause the resource stat tracking in the web UI to blow up, and it was causing big problems. And that's something we just dealt with 2 weeks ago. So those are some of the lessons we learned, and now I want to talk about some of the best practices that we've come up with to address those. I'm going to talk about how to use kernel remoting, using fewer, bigger clusters, knowing your workloads, isolating users, and scheduling resources efficiently. So the first thing, we just talked about how running all of your kernels and Spark drivers on the Jupyter kernel gateway is a real bottleneck. You want to distribute those into your resource manager, and that way you can run a lot more notebooks. But how do you do that? So one way to do that is with something called the Jupyter Enterprise Gateway. So this is a new open source project from IBM that builds on the Jupyter kernel gateway. It's a lightweight, multi-tenant, scalable, and secure gateway that enables Jupyter notebooks to share resources across an Apache Spark cluster. So now they will run inside a Yarn cluster in Spark Yarn cluster mode and get off your gateway server. Another benefit of this is that you get a lot of multi-user support. If you have Kerberos enabled on your cluster, you get secure communication. All kernel communication is encrypted, and you also get user isolation and user impersonation from Kerberos. Here's just a chart to kind of explain how that works. So you can see you have clients connecting, and they connect directly to the enterprise gateway. And now instead of all your containers running there, they work down in your cluster, which you can scale horizontally. And you can also see that they are running as their own users, and you can set up different access rights and permissions however you want. The next important lesson I want to talk about is using fewer, bigger clusters. So the first advantage of this is that you get the advantage of better resource utilization through statistical multiplexing. And all that is just saying that, on average, only a fraction of your notebook users are going to actually be using your cluster. So you can size your cluster for that average expected size and not for the maximum number of users that you're going to have. So an example where we didn't do this is at TWC, when we had a bunch of tiny clusters, we didn't get any advantage of that multiplexing. We just had servers sitting around not getting used. The only time when this doesn't work is if you have a job that just runs constantly. So if you know you have a lot of stuff like an ETL job that runs every 10 minutes or something, obviously the statistical multiplexing won't do anything for that either. Second, by having fewer, bigger clusters, you get improved security and auditing due to centralization. When you have a lot of one-off clusters, it makes it easier for bad practices to kind of slip in there. And third, it makes it easier for everyone in your organization to collaborate because everything is in one place. People don't have to keep track of different, URLs or anything like that. People can share their notebooks. Data sources can be set up all in one place. And if you have a catalog solution set up, people can see all the different data you have in your company, and they can figure out how to do stuff on their own, which is what you want. I also want to talk about knowing your workloads. So you want to know what kind of jobs you're running and what their resource bottleneck is. So if you have a hardcore machine learning job running, that might be CPU bound. But a lot of times you have ETL jobs and database jobs, and they're just IO bound or memory bound. And it's important to understand that because that makes a difference in how you want to schedule your jobs. If you know your jobs mostly aren't strictly CPU bound, then you can over-provision on the CPU. So say if you have 30 cores in your cluster, you can configure your resource manager to say you have 40. And this is because most of the time your Spark executor, nominally is taking one core, but really it's not really using that core most of the time. Memory, on the other hand, is less forgiving. Once you've used up your memory, you've used it up. In Yarn, for example, one way you can do this is you can use the default resource calculator, which will allocate resources only based on memory, not on CPU. And this can let you use all your cluster resources more efficiently. You also need to keep an eye on when you need to scale your cluster up and down. So if you are using Yarn, for example, you can watch for pending containers or preempted containers. And once you start seeing those, then you know you need to add more actual cluster resources. The last thing I want to talk about is the importance of isolating your users. So if you're like us, when you start out building your cluster, just your team's going to be using it, and it's okay if it all runs, if the cluster all has permissions to one Amazon account for your S3 buckets or something. But as you get more people and more data, this stops being tenable. So for example, at the weather company, we started out using Apache Zeppelin for our notebooks, and then we started out with one default user, which is kind of how it comes out of the box, or it did at the time, and you get one Spark context that everyone shares. And like, that's okay if it's just you, but once a lot of people are using it, it's a big problem. So we set it up correctly and started using Jupyter, which has multiple users, and that was a lot better. There are also a bunch of data catalog and governance solutions in the Hadoop ecosystem that you can check out that work with Hive, like Atlas and Ranger, and those let you keep metadata about your different data sources and set up different permissions for your different data sources depending on how sensitive they are. And finally, I want to say it's important that you get that figured out, because if you don't, then your users are going to just hard code like AWS access keys and like database passwords in their notebooks, which is terrible, right? Because that makes those really easy to leak out into the world. And now, Greg.
So the next thing up is talking about scheduling resources efficiently. This is mainly in the context of Yarn, but similar concepts exist in other resource managers as well. As we discussed a couple slides ago, separation of users is key to maintaining a stable cluster. It's advisable to take advantage of Yarn's hierarchical queue system to manage and organize your cluster's resources. It's actually tough to prescribe any one formula that works for every use case, but the queues allow you to assign a percentage of your cluster's resources to them. You can also set limits that will allow Yarn's scheduler to allocate more cores or more containers to a queue that are configured. For example, if you have a queue with only 10% of the cluster's resources allocated to it, you can set the user limit factor to 2, and the scheduler can allocate up to 20% of the cluster's resources to it. This is especially important if you're using dynamic allocation and Yarn's preemption together, as preemption only works between queues for now. We'll talk more about this later in regard to resource starvation. Another important point here to make is to take advantage of node labels to guarantee resource availability for jobs that have SLAs. Moreover, there's a lot of interesting work in the Yarn project around intra-queue preemption and asynchronous container allocation. These features should be available in Yarn 3.0. So this is a really simplified view of Yarn's hierarchical queues. As you can see, there's a root queue that has, like, the capacity of it is all of your resources. It has to be 100%. And in this example, I have queues A, B, and C, which have 30, 40, and 30% of the capacity allocated to them. And the user factors are set. So QB, for example, it's set to 2.5, and if no applications are running in A or C, actually one job running in QB could take up all of the available resources. And the hierarchy aspect of it is you can see queues C1 and C2 are children of QC. The next thing is dynamic allocation. Dynamic allocation will request executors based off of the scheduler's backlog. It will also shut down executors if they are idle for a pre-configured amount of time. This is great if you have users with unpredictable workloads and periods of inactivity, just like you do with notebooks. This can prevent them from locking up clusters' resources. You can choose whether executors with cached data hang around or get killed. By default, executors with cached data will not be killed. And still, if you have a workload that is known like a regularly run job, you should probably just use static allocation and avoid the dynamic allocation overhead. So now Brad's going to talk about some of the new work that we've been experimenting with.
Hey, so we've also had the privilege of doing some work on Spark to maybe address some of these issues we've been talking about. So the first thing we've worked on is recovering cache data when we're using dynamic allocation, and proactively shutting down executors to prevent starvation. So I worked personally on this first one, recovering cache data. So we talked a little bit about dynamic allocation, and dynamic allocation is really cool, but there's an issue if you cache your data frames, because dynamic allocation can't really deal with that. So what either happens is you just don't dynamically allocate those executors, they just live forever, or that cache data just gets dropped. And that can provide a bad experience for notebook users because you keep having to read data over and over again. So kind of my proposed solution, our proposed solution is that before we shut down those executors, we replicate any cache data to other nodes so that you can still take advantage of that cache data. So I've got some benchmarks that kind of represent like the best case for this usage scenario, sort of just like a proof of concept to see that this could work. In real life, it would obviously not be this dramatic. So just imagine, though, you have two users using your notebook service. One guy loads a bunch of data, transforms it, and go gets a coffee. Another guy comes up, he loads up some data, he go gets a coffee. The first guy runs some computations on his data, and then the next guy runs some computations. So they're just totally interleaves. You can see that we do get enhanced performance. So if you look at this graph, you've got, if you look at your initial data load, you've got the static case, the dynamic case, and then the dynamic case with cache recovery. So the two dynamic cases here are faster because they get to take advantage of more executors. So while the other guy is idle, the first guy can use a bunch of executors and load up all that data, whereas in the static case, they just have to split those evenly, and so they have less resources to load the data. And then, even more dramatically, when you're using that cache data, it makes a big difference if it's there, right? So you can see in the static and the recovered, it happens super fast. Because the data's already there. In the dynamic case, it takes a long time because they have to reread all the data. So if that sounds interesting to you, I would love it if you would check out my PR. I also have a Spark Jira you can look at. It's up there. Please check it out. Craig?
Okay, so preventing starvation is also one of the things we've been taking a look at. So there are times when notebook users are taking up all of the resources on a cluster. Actually, this is ideal. But if another notebook user logs in and tries to run a paragraph in this situation, obviously the resource manager won't be able to allocate any containers to the newly launched paragraph. The user will have to wait for resources and other notebooks to relinquish resources. Enter preemption. In Yarn, preemption attempts to gracefully request containers associated with over-allocated queues to shut down. The resource manager will send a preemption message to the application master that requests a very specific set of containers to be removed. The application master can choose to handle this in a variety of different ways. One, it can ignore it. This is actually what Spark currently does. The downside of this is that the requested containers to be removed will only be removed after a timeout. And by default, that timeout is 15 seconds. That's a long time for notebook users to wait, and keep in mind we want our users to not have to wait any more than 10 seconds. Two, the application master could actually handle the message and remove the containers immediately. This is better, but Yarn doesn't actually know anything about what the executors are doing. It doesn't know if they have cache data. So enter the actual solution that I implemented, which the application master can actually pick a set of containers to remove based off of its own criteria. The changes I've proposed, basically, it establishes a pluggable preemption policy, and the default policy will favor removing idle executors without cache data. And then if that is not enough executors to fulfill the request, then it will go to non-idle executors without cache data, and then finally preempt executors with cache data. And if you couple this with everything Brad's been working on with recovering cache data, you can imagine you'll have a more fully utilized cluster with happier users. I'm still working on the actual PR for this. The code's actually done. I just need some more testing. But you can keep up with the Jira and be on the lookout for the PR. So call to action. Go check out our Jiras and try out our PRs. As soon as mine's up there, you can try it out. And just a couple shout outs, because we'd be remiss if we didn't give thanks to those who helped us get here. Our colleagues Emily Curtin and Matthew Shower have been very instrumental in this endeavor. Emily is she's been working on SparkBench, which both Brad and I used in trying to test our stuff. So she's been working on Spark Bench, which is a wildly customizable benchmarking framework for Spark. So she is actually speaking on this tomorrow, so go check out her talk. And Matthew's actually been working on an instrumentation and visualization project called Spark Tracing that non-invasively instruments Spark, writes logs and events and RPC messages out to HDFS or wherever you want, and allows you to visually analyze in a Jupyter notebook, actually see all of the interactions that are going on. So if you're trying to debug a distributed application, it makes it a lot easier. And you can also easily pinpoint delays. So we're still awaiting open source approval for this, but hopefully you'll be able to go to that link soon and check it out. And also we can't thank VJ and Fred enough for our guidance and support throughout this process. And there's our contact information. If you need anything, just feel free to hit us up. All right, thank you.
Thanks.
Thank you, Brad and Craig, and thanks a lot for all the community contributions. We all appreciate that. We got about 3 minutes. Do you have any questions for Brad and Craig? There are 2 mics towards the end by the camera. Please walk yourself over there and fire away. Any questions? Going once?
Preferably
Twice.
true or false if you have one.
The people want to have coffee. I guess we should probably have coffee filters over here. Anyway, give a big hand to Craig and Brad. Thank you.